Beautiful place. I'm very impressed. This is my first time in Korea, so thank you very much. What I'm going to talk about, so I'm going to give two talks. The first talk today is on basics of two things. So I'm going to talk about basics of BGG. So today we will have BGG boot camp and also basics of hyperplane arrangements. So today is not such a good day because it's all basics and background. But I want to say right away, so then the reason I chose this topic was because of the topic of the conference. So at least Syzygies and exterior algebra are in the title. So there won't be so much sheaf cohomology, but it's there if you're interested in it. So I want to talk about the motivating problem. So before I even start showing slides, this problem that I'm going to discuss, hyperplane arrangements, comes from really topology. So the first people who studied hyperplane arrangements extensively were topologists. So there's a simple configuration of example of a hyperplane arrangement. I have 6 lines in the projective plane. And topologists are interested in the complement of, in particular, the fundamental group of the complement of a hyperplane arrangement in real space or complex space. So that's the object we're studying. Of course, it turns out that the fundamental group is quite difficult. And so you might say, what's the cohomology ring? So right away on the first page here, I have 2 interesting free resolutions. So Syzygies are appearing here. So this is the free resolution of the Orlik-Solomon algebra. The Orlik-Solomon algebra, which we will talk about later on, is the cohomology ring of the complement. So, and this is completely analogous to what we do all the time as algebraic geometers, where we take the resolution of some coordinate ring over the polynomial ring. Here I'm taking a resolution of a quotient of an exterior algebra over E. And those are the graded Betty numbers there. You can see they're pretty nice. And then there's another resolution that turns out to be very interesting, which is if I resolve the residue field. So if I take my cohomology ring with coefficients in K, then I can resolve the residue field over the Orlik-Solomon algebra. And these are the Betty numbers of that resolution. So I'm going to be interested in these 2 types of objects. So to set notation, even though this is a conference on Syzygies, and we're all experts in Syzygies, some of you far more expert than me, I want to set the notation. So here's the first example, just to set notation. So one time when I was a grad student, David Eisenbud said in a talk, there's only one example in algebraic geometry, the twisted cubic, right? So this is a proof of Eisenbud's statement. There's only one example. So here's the twisted cubic, right? So I embed P1 and P3 by using the 4 sections of O, P1 of 3, and we have a free resolution. So do I have a little pointer? Oh, I have a little pointer. So there's the twisted cubic is defined by these 3 quadratic polynomials, and then the Syzygies on those are given by the 2x2 minors of this matrix. And again, to set notation, we display this free resolution in compact form as a Betty table. So the Betty number in position ij, I is my x coordinate. I read over I, j is down. So in position 2, 1, I read 0, 1, 2, 0, 1. So position 2, 1 is Tor 2 in degree 3. So Tor 2 in degree 3, those are the Syzygies in degree, the first Syzygies, but in degree 3. So the linear first Syzygies, and that's exactly the 2, right? So B21 is the dimension of Tor 2 in degree 3. Those are our linear first Syzygies, and there are 2 of them, which we can see there. Everybody's okay with this. You guys should yell if this notation is not okay. Are we okay? So this is a lot of times I will write a free resolution in this form. So this comes from Macaulay 2. My advisor was Mike Stillman, who wrote Macaulay 2, so I have to use this notation, right? Okay, so there's the Betty table, and this is the example we just did. And the reason, and if you've ever wondered why the Betty table is written this way, is that the regularity, the Castelnuovo-Mumford regularity of your module, in this case M is S mod I, is simply displayed by this index here, because you're counting over and down. So when you do Castelnuovo-Mumford regularity, it's hi of f in degree I minus j. So the regularity here is 1, and of course the regularity is 1, which we know is the degree minus the codimension, which is part of the Eisenbud-Goto conjecture, which is at least true for curves, right? Everybody's good with this, right? So this is all notation. All right, so the first half of the talk now is going to be on BGG, but to talk about BGG I need to define Cazul algebras. So what's a Cazul algebra? So I have a tensor algebra on some vector space V, and I take a quadratic ideal. So I want to take an ideal generated by 2 tensors, so I is contained in V tensor V, And then if I have such an ideal, I can take its quadratic dual. So in the tensor algebra on V star, I can look at the ideal I perp, which consists of two tensors in the dual that annihilate my two tensors, right? So if A tensor B is an element of I, then I take the alpha betas that annihilate A tensor B. So this is called the quadratic dual.
Is it necessarily generated by decomposable tensors?
No, it's not necessarily generated by decomposable tensors. And in fact, we'll see an example in a second. And then we say that a quadratic algebra is a Koszul algebra exactly when all but the diagonal tors vanish. So if you don't like the tor notation, of course, what this is saying is that if I take the free resolution of the residue field over A, that resolution has matrices with only linear entries. So in particular, in Betti diagram notation, this says that my Betti table has only one row. So this is what's called a Koszul algebra. Now you might say, the reason I wanted to introduce Koszul algebras is they'll be important both for the topologists when we discuss hyperplane arrangements, but also you want Koszul algebras to set up BGG. So here's an example. The symmetric algebra, of course, is generated by the tensor algebra modulo these relations, xi, xj, minus xj, xi, right? That's how we get the symmetric algebra. And then the Koszul dual, or the quadratic dual rather, is easily seen to be xi, xj plus xj, xi. So the quadratic dual of the symmetric algebra is the exterior algebra. So I wanted to illustrate an interesting computation of using the Hilbert series. So here's a nice theorem about Koszul algebras that we'll see later on. That is that if you have a Koszul algebra, then its quadratic dual is also a Koszul algebra. And if you take the Hilbert series of the original algebra times the Hilbert series of the quadratic dual, but with a minus t inserted, you get 1. So let's do an example of this. So we've already seen that the symmetric algebra is a Koszul algebra. So the Hilbert series of the symmetric algebra on, say, 3 variables is just 1 over 1 minus t cubed. So there's the Hilbert series of the symmetric algebra. The exterior algebra on 3 generators, well, what's its Hilbert series? So in degree 0, I have the unit. In degree 1, I have E1, E2, E3. In degree 2, I have E1, E2, E1, E3, and E2, E3. And then in degree 3, I have E1, E2, E3, and that's it. So, of course, the Hilbert series for an exterior algebra is just a polynomial. It's not an infinite series. And so for the Hilbert series of the exterior algebra is 1 plus 3t plus 3t squared plus t cubed. That's what we just computed. And so if I take that, that's 1 plus t cubed. But if I plug in a minus t, I get 1 minus t cubed is the Hilbert series of this. And when I multiply those, I do indeed get 1. So this is an illustration of this nice property of Koszul algebras. So how do you show that something is Koszul? So if you were suddenly asked on an algebra test how to prove that, or if you were offered a prize. So I have, Frank Olaf was mocking me. I usually give coffee prizes for people who answer questions. But if you wanted to prove that some algebra was Koszul and you had a computer handy, the easiest way to check that an algebra is Koszul is to compute a Grobner basis. So if your ideal has a quadratic Grobner basis, then the algebra is Koszul. And the reason for this is rather easy. So Betti numbers are upper semi-continuous. So if I have a quadratic ideal and I look at it has a quadratic Grobner basis, that means that the initial ideal is also generated by quadrics. But it's generated by quadratic monomials. And it's an easy old result of Froberg that a quadratic monomial ideal is Koszul. So using upper semi-continuity, all you have to do is compute a Grobner basis. If the Grobner basis is quadratic, you're good to go. Of course, there's a problem there in that there's lots of different term orders. So you'd have to find the right term order. You could say, well, I could look at the state polytope, which encodes everything. That's possible. But even then, this direction does not go the other way. So there are examples of algebras which are Koszul, but which do not have quadratic Grobner basis. The easiest one, the first examples I know of are in a paper of Eisenbud, Reeves, and Totaro. They're kind of interesting. They're quadratic complete intersections that don't have quadratic Grobner bases. But the easiest one to write down is this one of Giulio. So if you take the pinched Veronese, so if I take So if I take the Veronese V3 contained in P, what is this, P9. So the triple Veronese embedding would use these 10 monomials, right? If I use something like S cubed, T cubed, and U cubed, and so on, I get the triple Veronese embedding of P2, right? But if I don't use all the sections of, I'm using H0 of OP2 of 3, right? So these are the sections over here. But if I don't use a complete linear series, that is, if I omit STU, then I still get the image of this is still generated by quadratics. It's easy. Everybody knows that the triple Veronese is generated by quadratics. But if I omit this section, so I use an incomplete linear series, I still get an image. Now, this is sort of, let's call it PV for the pinched Veronese, which now sits inside P8. Then that is also a Veronese. So the quotient is a Veronese. Is a Cazul algebra, but it doesn't have a quadratic Grobner basis. So that's just an interesting example that says you don't always have such things. So we've talked about Cazul algebras. We know how to prove that an algebra is Cazul. So now it's BGG time. So this is our Bernstein-Gelfand boot camp. So I have the symmetric algebra and the exterior algebra. And so BGG is an isomorphism between the derived categories of bounded sheaves on PV and bounded complexes of finally generated E modules. So this is all fancy sort of, well, at least for me, whoops. This is sort of a fancy type of BGG. I want a blue-collar BGG. So I want BGG for the working person. So I can get functors R and L, which do the following. So R will eat a finitely generated graded S module, or if you like, a coherent sheaf on projective space, and spit out a complex of linear free E modules. So I take an S module, it gives me a complex of E modules with linear differentials. And similarly, L does the same thing. It takes a finitely generated E module and spits out a complex of S modules with linear differentials. I'm going to do this in a second, so this is all just words. So why would you want to do this? Well, certainly if you hand me a coherent sheaf on Pn, I can look at the sections in any particular degree. That's a nice vector space. And I can take the gamma lower star of that. I have a graded object, right? So if I want to study the graded pieces of that, I really would like not just a bunch of vector spaces, but I'd like to relate those vector spaces with some sort of a differential. And what BGG does, in some sense, is it encodes the multiplication map in the differential. So that's a way to think of it. So this is sort of extracting. So this is the point of BGG is this is one way if you want to analyze a coherent sheaf on projective space. One way to analyze it is by using this BGG correspondence and looking at E modules. So one of the things I'll discuss, it'll appear, I think, more prominently in Frank's talk, but I'm going to discuss briefly Tate resolutions, which is a way, a very fast way to compute sheaf cohomology. So if you want to compute sheaf cohomology fast, BGG leads to that, is one way of doing that. All right, so that's the sort of background. But now, I want to do an example. But I want to do this since I have blackboards. I'm sorry, you guys get subjected to this. If we have blackboards, we should use them. So let's do BGG. Let's do this R. Let's do L. So let's do BGG for E equals wedge 3 of K. Let's just save K. So I'm going to take an exterior algebra on 3 generators, and I want to find out what is this L. I was checking to see if people were sleeping yet. Any errors that I make are always tests. So Frank is now exempt. Now I won't call on Frank. I won't call on any professors, but some students out there. I know there's some students. So what is L of E? So I have to tell you, I didn't need, so this was some abstract thing. I haven't told you how to build the differential. So what is this L of E? So in general, let me say instead for, let's say that P is an E module, L of P. This is an E module, a graded, finally generated graded E module. What I do to make the complex is I take the pieces, and I want to say one thing actually here. S is sim V dual. This is going to be graded in degree +1, like we usually grade the polynomial ring. So when we do then E is wedge of V. This is going to have degree -1, right? So the generators, so I'll let my variables up here be xi are the variables here, and ei are the variables in the exterior algebra. Everybody's with me, right? So I want to grade the exterior algebra negatively, symmetric algebra positively. So what do I do with P? So P is just going to be the complexes. I'm going to have P sub I plus 1 tensor S, p sub I tensor S, p sub I minus 1 tensor S. So all that I'm doing to build my complex is I'm taking graded pieces of my module. That's a pretty natural thing. I tensor with S. And all I have to do now is tell you what the differential is. And the differential is just wedging. So the differential D, down here, D sub I is just wedge with summation xi tensor ei. So I take this element, which is the variables of the symmetric algebra times the variables of the exterior algebra, and I wedge it. So let's build this for the exterior algebra. So for the exterior algebra, for our example here, so my graded pieces, of course, are going to be, I'm going to write it this way, K and let's write some bases down here. So here the basis will be 1. Here the basis is E1, E2, E3. Here my basis will be E1 wedge E2, E1 wedge E3, E2 wedge E3. And here my basis will be E1 wedge E2 wedge E3. Everybody's with me. You guys in the back, can you see this okay, or am I writing too small? You should yell if it's too small. All right. So I write the easy one. I do the professor, when I'm teaching, I always do the easy one first. So this one, so the unit here, 1 goes to summation xi ei from 1 to 3. With respect to this ordered basis, E1, E2, E3, that means that this differential just takes the form x1, x2, x3. So that was kind of stupid and easy, right? Everybody's with me here, right? The 1 goes to summation xi ei. That's that. So let's understand what goes on here. We've got nice space. Let's put our space over here. So where does E1 go? And I should say, one has to be careful. As long as you're consistent, it's going to be important which side I wedge it on, right? Because it's an exterior algebra, if I wedge on the right or left, as long as you're consistent, it's fine. So let's say that the multiplication, let's say this is wedge. Let's do it this way. Wedge with my input. So then if I do this, where does E1 go? E1 goes to x1, E1 plus x2, E2 plus x3, E3, wedge E1, which is going to be what in terms of this basis? So this is, of course, the E1 wedge E1. This piece is 0. So I get x2, E2, E1. I'm going to not write the wedges, plus x3, E3, E1. But with respect to this ordered basis, E1, E2, E3, I should write that as x2 times E1, E2, and minus x3, E1, E3. So with respect to this ordered basis, I'm going to have, oops, I lost my minus sign, right here. So I have a minus x2, a minus x3, and a 0, right? So that's my first column. Now I did that one. You guys have to help me out. What is the next column going to be? Somebody who is not. So by the way, part of the thing, it's kind of embarrassing because part of the results that I'm going to mention on the next slide or two are due to either Frank Olaf or Gunnar. And so I have some of the world experts on BGG in the audience. So they're not allowed, world experts are not allowed to answer. They don't win prizes. So somebody who is seeing BGG for the first time, if there is any such person, what is my next thing? So I want to know, where does E2, so my ordered basis here, the next column, this is E2. So E2 maps to this wedge E2. You guys have to tell me. Help me out. Remember, the other good rule is that if you answer early on, then you're exempt. It's like these Survivor shows where you get immunity, right? So when I wedge this against E2, I get, I'm shutting up. You guys, you're going to be, if you guys don't help me out, we're going to be stuck here. So when I do this wedge this, I get 0, right? Because E2 wedge E2 is 0. So this term won't matter. So I've got this wedge this and this wedge this. So how do I write that as a vector? I heard somebody say x1, E1, E2, right? So that's that times that. This one is 0. And then I have x3, E3 wedge E2. But of course I have to flip the sign here, so this stays plus minus x3. Right, so in terms of the ordered basis over here for E2, I've got an x1 here, and then I have a 0, and then I have a minus x3. So then the last one, E3, when we do E3, of course, again, this is now this is easy, so I'll zip through it. So I have x1, E1, E3, plus x2, E2, E3. And then the last one, 0. So in terms of our ordered basis, I have a 0, I have x1, and I have an x2. So there's our second differential. So we've calculated that differential OK. Let's do the last differential just for fun. So the last differential, I'm sending E1, E2 So you can see when I wedge this against 1, 2, let's write this, let me write it more carefully. So when I wedge this, E1 wedge 1, 2, this one is 0, right? Because I've got E1 wedge E1. This one is 0, E2 wedge E2. So all that I get is x3, E3 wedge E1 wedge E2. If I bounce my using this basis, I bounce my E3 1, 2, so I get 1, 2, 3. So that one is going to be, in terms of the ordered basis, I get an x3. Let's do the next one. When I do the next basis element, 1, 3, well, 1 wedge 1, 3 is 0, 3 wedge 1, 3 is 0, and I have an x2, so I get x2. But now I have E2 wedge E1 wedge E3, right? This is here, so I have to flip it once to get it ordered. So I have a minus x2. And then when you do the last one, let's do E2, E3, E2, E3. When I do the last one, when I wedge this, these two are both 0. I get x1 wedge E2, E3, E1, and I bounce this 2 steps so it doesn't change the sign, and I get this. So that's it. So we've got all our differentials. So we've done BGG for an exterior algebra. And of course, the point is that this, as Syzygies people, this makes us very happy, right? Because what we see is that when I BGG an exterior algebra, all that I get is the Kazul complex, right? So BGG of an exterior algebra, so let's write this down for our first example. BGG of an exterior algebra of wedge Kn is the Kazul complex. Let's write Kazul complex n. So it's just the Kazul complex and n variables. So it's an easy exercise to prove this. So this is kind of nice. So this is already telling you something, right? If you wanted to compute Kazul, you can see that you're going to be computing Kazul cohomology. You could take and you could tensor your module with this the L of the exterior algebra, and that's going to compute Kazul cohomology for you, right? So, lost my clicker. Maybe I have to. All right, maybe I have to give a prize for someone who finds my clicker. Ah, here it is. Okay, so this is the example that we just did. So now, let's do one more example. So I really want to make sure that we feel comfortable with BGG. This one is bad because there's a typo on the board. That should be a minus n there, and there should be minuses with all the things down here. But let's go through this. So this one I won't do on the board. So let's do the R functor. So here I take a modular of the symmetric algebra, And I'm going to apply, this is a little different. So this E, whereas I just tensored with S, here I have to tensor with the K dual of E, which is Hom of K of E into K. And so that turns out to be, this is a minus n. So E dual is just E, but with a shift in grading. So R of M is, you can write this, I guess, sort of functorially as Hom K of E into M. Let's do an example. So if I take this very simple S module here, so I take polynomial ring in 2 variables, modulo this little toy ideal, I have these pieces. These should be hats, too. There should be hats on these E's here. So these E's, you don't see them. There's hats, but they're very, very small. I used a really tiny font for the hats here. Come on, somebody has to laugh. So the exact same process. So 1, the unit here of S goes to E0, X0, E1, X1. But now in terms of the bases for S, or for my module M, maybe I write it over here. Give this some time. Oh. So here, my module M is K of X0, X1, mod X0, X1, X0 squared. So the graded pieces are going to be, let's write bases. Bases for the pieces of this are going to be 1, X0, X1. But then in degree 2, I've got X1 squared. In degree 3, X1 cubed, and so on, right? So the dimensions of these pieces are 1, 2, 1, 1, and so on. So my complex is going to be a complex of E modules of ranks 1, 2, 1, 1, 1, and so forth. And then when we write out the multiplications, so the only interesting multiplication is really this one right here. So let's see what's happening here. So that's this multiplication. So the first multiplication map is stupid. This 1, so 1 goes to X0, E0 plus X1, E1. So that's going to, in terms of this basis, X0, X1, that's given by the matrix E0, E1. So that one's obvious. Let's do this next one. So what about the next one? The 2 basis elements here, X0, X1, X0, I don't have to write them out because they're already written out. So X0 goes to X0, E0 squared plus E1 times X0, X1. This is 0, and this is 0, right? Those are both 0. And so X0 gets sent to 0, so I have a 0 for the X0. X1 goes to E0 times X0, X1 plus E1, X1 squared. And again, with respect to our ordered basis, this is 0, but this is an E1. So I get an E1 there. So that's the map. And then the rest of the way out, it's E1s, right? So this is the complex for R of M. So what, you say, very reasonably. So what? So let's see why this is interesting. So it's exact except at the second step. How do we see that? Oops. Of course it's exact, right? The kernel of this multiplication is just E1, right? The kernel of if I multiply by E1, the kernel of an E1 map is just E1 itself. So it's exact way over here. Exact, 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 exact. Interesting thing. This clearly has a big kernel, right? So there's a big kernel right here, but there's an image. So let's compute. I want to compute the homology. This is a complex, so I want to compute the homology. Let's compute the homology right here. So you guys have to help me. Again, remember, there's typos here. This is really a -3. So let's compute the homology. Let's compute H1 of R of M is equal to, well, it's the kernel mod image. So what's the kernel of that map? So the kernel is clearly going to be generated by 1, 0. But there's something else in the kernel. What else is something that's in the kernel? Help me out. There's an obvious other thing in the kernel with a 0 here and something here. Remember, we're exterior algebra. What could go here? I want the kernel of this. So if I take 0 E1 times 0 some mystery element, alpha, it's going to be 0 plus alpha E1. When could this be equal to 0? exterior algebra, right? So alpha has to be, help me, alpha has to be E1, right? So there's something else in the kernel. And it turns out that that's the whole kernel. So I've got this is my, those generate the kernel, mod the image. So the image of the previous map is E0, E1, right? So if we write this down, let's think about what this is. Let's call these generators alpha and beta. So what I've got is H1 is alpha and beta. But then I have this relationship. This relation says E0 times alpha plus beta, right? I can write this. This is equal to E0 times 1, 0 plus 0, E1. Everybody's with me here, right? This is E0 times 1, 0 plus 0, E1. So this can be written as E0 alpha plus beta. So this immediately says clearly beta is a consequence of alpha, right? So I can kill that generator, right? And so I'm left with alpha mod E0 alpha, except that clearly if I multiply this thing by E0, I get 0. So what I get at the end of the day is I get alpha modulo E0 E1 alpha. So this is my H1. So what is this? This alpha, this generator, is in degree, remember the degrees were messed up, this lives in E minus 3. So this is isomorphic to E minus 3 modulo the relationship E0 wedge E1. So this is a complete description of the H1. Why do we care? Why would we care about that? So let's see why we would care. So again, typo right there. This is all right, but that's a minus there. So here's a beautiful theorem of Eisenbud and two other guys. So here's a result of Eisenbud and two other guys that we can compute the tors of a module over the symmetric algebra as the HIs of Rm. Okay, so I'm encoding these things here. So let's see if this is true. Let's test. I don't know. I'm a little skeptical about a theorem proved by these three guys. So let's see if this theorem is true. How am I doing for time, by the way? How far am I in? I have my thing over here. We should be close to halfway. Oh, I'm a little past halfway. Got to speed up. Okay. So the free resolution. So these are supposed to be tors. So m was equal to s mod x0 squared x0 x1, possibly permuted, but I don't really care. So the Betti table of this will look like 1. I have 2 quadratic generators, and I obviously have 1 linear syzygy on this. So here's my Betti table. So tor 1 of mk in degree 2. These are my quadratic generators. This is going to be a 2-dimensional object. I guess I could say the dimension of this. I'm writing 2. And then tor 2 mk in degree 3 is 1. I'm just writing the dimensions, right? Those are the dimensions there. So according to this theorem, my tor 1, so this tor 1, 2, tor 1 in degree 1 plus 1. So tor 1 in degree 1 plus 1 should be H1 in degree 1 plus 1. So what is H1 in degree 1 plus 1? So what is this thing in degree? So I want to compute this in degree 2. So what's the degree 2 piece of this? So the degree 2 piece of this is exactly E mod E0 wedge E1 in degree minus 1. But what's the degree minus 1 piece of this thing? Remember, this is negatively graded. Because it's negatively graded, the generator is in degree 0. The variables, E0 and E1, are in degree minus 1. And I have 2 of them. So in fact, I have exactly the right count here, right? This thing in degree minus 1 is a 2-dimensional vector space, which is exactly what we should see there, right? And similarly, exercise, do it for the other one. All right, so that's a nice theorem illustrating one of the uses of BGG. So now I wanted to mention the Tate resolution. So what is this Tate resolution, which we will see later on? And this is my 2 pages on computing sheaf cohomology using BGG. So what you do, you have a coherent sheaf. We know that there's many modules that give rise to the same coherent sheaf. But all that I'm going to care about is taking a high degree truncation. So if I take a module whose sheafification is f, and then I truncate it in degree greater than the rate. Oh, I missed a statement here. Oops, sorry, my bad. So in particular, I didn't mention this corollary. So there's this, because of this, this says the corollary is, of course, that you can capture the regularity of M. Well, regularity is measured by this tor, but this tor is this Hj, right? So as soon as this complex is exact, that means that you're past the regularity. So once you get past the regularity with this R of M complex, it's exact. So what we do is we take a module representing our coherent sheaf. I go to the regularity. So I have this complex, and I truncate it. So I truncate it when I'm past the regularity. This is exact by the theorem. So this piece of the complex is exact. And then I do a splice map. So I can take the kernel of this map, and I can take a resolution of the kernel, and now I have something which is exact in both directions. By the way, I built it. This is exact by the theorem. This is exact because it's a resolution of the kernel. So this is the Tate resolution. And so what I have is this, this infinite complex going both ways. Here's a little quick example of the Tate resolution. If we just do the Tate resolution to S, S has regularity 0. So I'd be looking at something like this. Right? So my first map, I'm going from E to e to the n. This is a vector, say, e1 up through en. And I have to take the kernel of this map. So the kernel of this map is easily seen to be just e1 wedge en. Right? So the kernel of this map is generated by this. So this is my splice map. So I have e1 to e1, and then I take a resolution going back, and I see something that goes the same way in both directions. So this is an example of that for the polynomial ring itself. So here's the last theorem I wanted to mention on Tate resolutions. This is also due to David and Gunnar and Frank Olaf. What's beautiful is that the modules that appear, so of course, as soon as I define this Tate resolution, what you guys should have been saying is, why do I care about the Tate resolution, right? What good is this to me? And the good of the Tate resolution is right here in this beautiful theorem. So the modules in the Tate resolution are built exactly by pieces of the cohomology of F. So I take the cohomology of my sheaf, and then I'm tensioning it with E hat, and I take a direct sum of those pieces. So I want to do this backwards a bit. So suppose that we take, from our running example, which was the twisted cubic, I take OP1 of 3. That's what I used to embed. That's my OX. And so it's trivial. We all know how to compute the H0s and the H1 of these. So the H0s of this are just H0 OP1 of 3i, and so that's 3i. So those are the dimensions of this H0. So I'm going to encode those dimensions here. This is just the Hilbert function of the twisted cubic. So I see 1, 4, 7, and so on, 3i plus 1. Similarly, just use duality. I can compute the H1, so I see these things. So this is, I can now see what my Tate resolution is going to be. So this is one regular. We already computed the twisted cubic was one regular. So I have exactness from here on out. This map, though, has a kernel. And in the kernel of this map, this map has a kernel. It's exact from here on out. This has a kernel. The kernel includes this, which is a vector of the variables, but there's also two quadratic relations. So what happens, the splice map is really encoded by these two things. So the kernel of this first map right here is a 3x4 matrix with one column of linear entries and two columns of quadratic entries. So this was going backwards, and you should very reasonably say, well, that's not very interesting to me because you're telling me that this Tate resolution is good to compute cohomology. The point is that you can tell Macaulay 2 or some other computer algebra system to compute the Tate resolution, and from the Tate resolution you can then read off the cohomology. So, and in fact, this example is stolen right out of David's book on geometry of Syzygies. So you should go and look, except there's some typos in there when he writes it down, so you should tell the computer to do the resolution and look at it. All right, so that was very fast BGG boot camp. And so the second part of the talk is on, there's a famous TV show called Monty Python's Flying Circus. And he has this thing where he says, now for something completely different. So we're completely switching gears. So for those of you in the very back who were falling asleep, I saw Hero's eyes shut. It's okay. Some of us have an excuse. If you came in at 11 o'clock last night from the US, you have an excuse to fall asleep. So here's hyperplane arrangements. So this is, in some sense, this is very, very visual and combinatorial. So what I want to convince you guys about hyperplane arrangements is that there's something that, on the one hand, are very simple combinatorial things that you can get your hands on, but there are very interesting topological questions that are encoded in Syzygies over the exterior algebra. So easy to visualize, but fun computation. So what is a hyperplane arrangement? Well, the definition's there. You hand me a bunch of hyperplanes. Typically, I will be thinking over the complex or real numbers, so I have interesting topology. I will just mention that if you work over finite fields, there's all sorts of interesting enumerative questions here. But I'm not going to do, I just want to stay topological now. So I have a collection of hyperplanes in real or complex space, and then their arrangement is the collection of those hyperplanes. And what we're interested in is the complement. So I have a bunch of hyperplanes. That's the complement is a topological space. And here is the quote that I always include in my talks on hyperplane arrangements. So here's a quote from Hirzebruch. The topology of the complement of lines in P2. I mean, what could be simpler? Lines in P2. The topology is very interesting. He probably said c'est intéressant. The investigation of the fundamental group, very difficult. So this is great, right? So I've got a line configuration in P2, a simple combinatorial object, and Hirzebruch is already telling us this is a hard problem. So here's some intuition for this. If you remember Zariski, there's a beautiful example of Zariski where if you take a sextic in the plane with 6 cusps, if those 6 cusps lie on a conic, 6 points in P2, right? Either the 6 points lie on a conic or not, the topology of the complement differs depending on whether the 6 cuspidal points lie on a conic or not. So you could guess, right, that there's interesting geometry coming in here. So that's Zariski's example. Anyhow, so in an old Invenciones paper, so this is from, what, 36 years ago, Orlik and Solomon gave a beautiful description of the cohomology ring. So notice this is right, here's a question about fundamental group. So I'm going to skip fundamental group for a second and go to the cohomology ring. And it's determined by the intersection lattice. I'm going to say what that is on the next slide. So this is a lattice in the sense of a graded Poe set. So lattice meaning I have a Poe set, a partially ordered set. At the bottom of the lattice is the whole ambient space V. At the top of the lattice is this thing that the lattice people call 1 hat. And then the elements of rank 1 are the hyperplanes. So we say that an arrangement is central if all the linear forms are homogeneous. Of course, if they're homogeneous, you actually have an arrangement in projective space, right? These are in projective space. And so, and you also call an arrangement essential if the common intersection of the hyperplanes is the origin affinely. Of course, if it's the origin in affine space, the intersection's empty in projective space. So in terms of studying the topology of the complement, we will always make these 2 assumptions. And what that means is that I'm going to be working in projective space. And this essential supposition means I can always assume that I have the coordinate hyperplanes there. So after a change of coordinates. So that's what our situation is. Here's an example. So this is one of the sort of most interesting examples in the study of arrangements. So if I take the reflecting hyperplanes of SL4, those are the xi minus xj's, where 1 is greater than I, less than j, less than 4. So I have these 6 hyperplanes in 4 space. Now, if you're interested in topology, you can see that there's a common linear subspace, right? If I take the span of 1, 1, 1, 1, that's in all these hyperplanes. And so from a topological perspective, I have a trivial factor. So what I do is I project down orthogonal to that space. So when I project orthogonally to that space, I get an arrangement in 3 space, which is still central, so I can view it as a collection of lines in P2. So this is called the braid arrangement. So I've drawn the picture of it here. So here's 6 lines in P2, and this is the intersection lattice. So this was what I was talking about. So the ambient space is at the bottom. I'm being a little schizophrenic because I'm drawing this in P2, but my intersection lattice is in C3. Then I have my 6 hyperplanes here. The rank 2 elements, that's the codimension 2 intersections. So for example, right here, where hyperplanes 1, 2, and 3 intersect, that's this rank 2 element. This is codimension 1, codimension 2, and so on, right? So this is the intersection lattice. So, that's I have this intersection lattice, and it turns out that what's great is that all of the cohomology ring is encoded right here. So let me tell you what the cohomology ring is. Actually, I'd tell you 2 enumerative invariants first. The Mobius function is just assigning to each point of that lattice a integer, so given by this recipe, and then the Poincare polynomial encodes those things. So let me say in plain English what this is. So I said there's a lot of definitions in this part of the talk. So let me go back for a second. I'll give these slides to our conference coordinator, and they can pass them out. So you don't have to take pictures if you don't want. So what this Mobius function does, all that it says is the Mobius function is 1 here at the bottom, and then it's defined recursively. The Mobius function at any point plus the Mobius functions of everything below it has to add to 0. So that means if it's 1 here, every hyperplane is assigned value -1. And then at a normal crossing, -1, -1, 1. So normal crossings get assigned value 1. A triple point, I have 1, 1, 1, or -1, -1, -1, and a 1. So a triple point would be -2, and so on. So the Mobius function is defined recursively. And then this last thing, this Poincare polynomial, what you do is you take the Mobius functions and you multiply them by t to the rank. So in particular, for the example that we just had, we said the hyperplanes, which were at rank 1, they all had Mobius function -1. So for my hyperplanes, I have 6 times -1, but then I have a -t. So -6 times -t gives me a 6t. Then for the triple points, these are each 2. So I have 2, 2, 2, 2. That's 8, 9, 10, and 11. So that's the 11, and then the last thing is a consequence of this. So this is the Poincare polynomial. Now, you should say, why do I care about this? So this is interesting to the combinatorialists are interested in this, but the point is that this Poincare polynomial really is the Poincare polynomial. By what I mean, this encodes the ranks of the cohomology. So this is kind of cool. That means that the cohomology ring, I haven't told you the ring structure, but it's telling me that the dimensions of the cohomology ring can be read off just from this combinatorial data. So this is H0, H1, H2, and H3 of the cohomology ring. So that's a theorem. Here's the actual presentation of the cohomology ring. So the cohomology ring is, I take an exterior algebra, and I have a generator for each hyperplane. So I have a exterior algebra, generator for each hyperplane. And what is the ideal? So what is this ideal I mod out by? Anytime I have an overdetermined intersection, so if I have R hyperplanes should meet in codimension R, right? A single hyperplane is codimension 1. 2 hyperplanes are codimension 2. 3 hyperplanes should be codimension 3 if they're generic, but they don't have to be generic. I need one more hand here, right? So I could have 3 hyperplanes meeting in codimension 2. So if I have an overdetermined intersection, anytime I have an overdetermined intersection, I take the product of all those things, and then I just do this alternating sum of leaving one out, just like a simplicial boundary operator, right? So this is the relation. So this is called the Orlick-Solomon ideal. So let's do it for our example. Oops. So for our example, we have these things aren't going to contribute. Those are codimension 2 intersections with 2 hyperplanes. They're not interesting. But these guys are interesting, right? These are 3 hyperplanes intersecting in codimension 2. So each of those triple points, each of the triple points gives us a relation in our cohomology ring. So what do we see? So 1, 2, 3 was a triple point. So we have 1, 2, -1, 3, plus 2, 3. And similarly for the other 4 triple points. Now, we're in P2. 4 hyperplanes wanted to intersect in codimension 4. There is no codimension 4. So I have all these other relations. But it turns out in this example that these other relations are consequences of I2. So I don't need them. So I have this nice algebra. And let's just check. So let's see if what I told you is true. So I have an algebra with 6 generators. So certainly this 6 is right. But let's check out the degree 2 piece. So the degree 2 piece, it's an exterior algebra with 6 generators. So the exterior algebra with 6 generators is going to have 6 choose 2 equals 15. But then I've lost my 4 quadrics. So 15 minus 4 is 11, which is indeed the 11 here. So this is sort of a stupid quick check that this really is the Poincare polynomial. All right, so this is the object that I'm going to be really interested in for the remainder of today. And like I said, we won't have too many theorems today, but especially one of the things I like about talks is when there's lots of open questions. So if you like at least 2 of the topics of the conference, which are Syzygies and exterior algebras, I will give you guys lots of interesting open questions, okay? So that's where we're going in this context of hyperplane arrangements. So, all right. So here's the last part of the talk. This is the hardest part of today's talk. So I want to talk about the original topological motivation. So we know what the cohomology ring is, right? So I said that the fundamental group is difficult. So if we have any group, you hand me any group, nothing special right now, I can form the lower central series. So this is something we learn in Algebra 1, right? I take the brackets of the group with itself and form this chain of normal subgroups. So this is the lower central series of a group. if I have such a lower central series, I can take successive quotients, I can tensor with Q to kill torsion, and this gives me actually something that's a graded Lie algebra. So I want to look at this graded Lie algebra for the fundamental group. And I want to look at the ranks of these pieces, right? These are now Q vector spaces. I want to look at these ranks. These are called the LCS ranks. So if you're interested in studying these in a particular context, we're interested in understanding the fundamental group of the arrangement. And I'm going to completely cheat. So down here, the fundamental group, I gave you this nice presentation for the cohomology ring, right? You can read it right off the intersection lattice. So it's combinatorial. It's like a Stanley-Reasoner type ring. The fundamental group is much more delicate. So there's a lot of presentations for it. So you know the generators and relations. Of course, I remember some topologists saying once, it's almost worse if you have a presentation because then people expect you to be able to do something with it, right? So there's presentations. The first thing I want to highlight is it's not combinatorial. That means that there are arrangements which have the same intersection lattice. Combinatorial means sort of this, the combinatorial way that the hyperplanes intersect. There are examples, not the first one you'd think of. The first one you'd think of, at least for me, would be to do something where I have some intersections of lines in P2 where 6 intersection points are on a conic. That's not the example. It's 15 lines in P2, but the fundamental group's not combinatorial. So the idea is, if you want to study this complicated object, what we're going to do is try to probe it by studying these invariants, right? So I want to study these lower central series ranks. This is hard, so I want to study something related, these LCS ranks. And it turns out that these LCS ranks, if you take successive hyperplane sections, you don't change the fundamental group of a complement. So we're going to be studying these LCS ranks for an arrangement in P2. So that's what we want to do. So this example, the example that I had all the way back, where's our example? Here. I want to focus on this little example, 6 lines in P2. So for 6 lines in P2, if you plug this presentation into gap, so you can honestly do these computations. The phi k's for that example are 6, 4, 10, 21, 54, and it goes on forever. Okay? So what? You say, this is something, I could be making this up. This does not speak to me. You should be thinking, yuck, I don't know what these things are. What I want to do is I want to take these LCS ranks, and I want to stick them into a formal power series in this form. So I want to take my phi k, and I make it the power of 1 minus t to the k. So 6, 4, 10, 21, I put in as 1 minus t to the 1 to the 6, right? That's the first. 1 minus t squared to the 4th. 1 minus t cubed to the 10th, and so on. So I do this. I make some hideous, disgusting. This is the topologist that I should say, I'm not responsible for this. This is the topologist who did this. So I take these phi k's, I put them in this, and then I expand this. So if I expand this formal power series, I see this thing, which still probably doesn't look very nice, except for 2 things. First, I want to point out, if I multiply this thing against this, let's take the Poincare polynomial and put in a minus t. Here's my Poincare polynomial. If I multiply this thing against this, what happens? Well, I get a 1. The 6's cancel out, so I got 0 for the t coefficient. What about t squared? 25 minus 36 plus 11. Well, 25 plus 11 minus 36 is 0. The t squared coefficient is 0. What about t cubed? 90t cubed minus 150. 90 minus 150. What about, what's next? 6 and 11 plus 66. And what's the last one? 90. Let's see. 90 minus 150 plus 66 minus 6. What do we get? 156 minus 156, 0. So in fact, when you multiply these 2 power series together, you get what? So this times this is equal to 1. So this times this is equal to 1. This should remind you of something where we plug a minus t in. This is actually the Hilbert series of something. This is the Hilbert series of my Orlick-Solomon algebra with a minus t plugged in. And when I multiply that by something, I get 1. This is saying this thing has to be some kind of Kazul, this has to be some kind of Kazul dual algebra. That's really, so somehow there's some Kazul dual algebra floating around in the picture. And that's exactly what's the case. So, oops, wrong way. So here's a theorem of Kono. This is an Invenciones paper from, again, maybe 30 years ago for the reflecting hyperplanes of SLN. That's this braid arrangement. you have a formula. This is exactly the formula, right? So the example that we just saw generalizes to the reflecting hyperplanes of SLN for any n. But in fact, the real thing that I want to point out, you should be saying, where's the Syzygies? And so the Syzygies, I want to point out something. Oops, wrong way. Look at this. Here's these numbers. Here's these numbers right here. We want this to be the Hilbert series of something. Well, let's see what we've got here. Let's go way back, way back, way back, way back, way back, before you knew anything about, or you hadn't heard any talk at all. Look at the tors of the residue field over the Orlick-Solomon algebra, 1, 6, 25, 90. That's them, right? So these are our Syzygies. This is the resolution of the residue field over the Orlick-Solomon algebra, and they're given to us in that form. So fast forwarding, so where are we now? So that's the theorem. So I didn't compute them, but we could tell the computer to show these things, and that's exactly what those numbers are. So those are the tors. So this formula that I had on the board of Kono. The topologists are very interested in these lower central series formulas, and so there's a whole lot. I'm just going to flash them up there. This is all for hyperplane arrangements. So there's lots and lots of results for hyperplane arrangements, and the topologists are very interested in them. So my point would be, if you want to make yourself popular with topologists and you like Syzygies, prove some theorems of this type. So these are a bunch of classes of such arrangements. I should point out, the one that I want to really highlight is this last thing. There's a result of Arena-Pava, which shows that you won't always have such a nice rational generating function. So you can't always do it for hyperplane arrangements. John Eric Roos also has some papers on this. But the last part, 2 slides. So I want to relate this to some Lie algebras. So we had this Lie algebra G that we took by forming the lower central series. There's another Lie algebra called the holonomy Lie algebra. So the holonomy Lie algebra, what I do is I take my H1, take a free Lie algebra on it. Okay, so H1 is just a vector space. I can take a free Lie algebra. And when I look at the dual of cup product, so cup product takes me from H1 to H2. The dual of the cup product map gives me a map this way, and it has an image. Oh, sorry, cup product this way gives me an image, and Chen defined this thing called the holonomy Lie algebra. So it's the quotient. I take the free Lie algebra, and then I look at the image of this multiplication map. So Kono proved that this is all in the context of hyperplane arrangements, that this is a really nice sort of, if you're not a Lie algebra person, it's fine, but what I've got is a really nice description of the relations on this Lie algebra. It's a free Lie algebra on some generators, modulo these relations where what do? Anytime that I have a dependent set in codimension 2, I only care about 3 hyperplanes intersecting in codimension 2, or 4 hyperplanes or so on, I take the bracket of that. So those are my relations. So what you say? So what Kono proved was that the phi k's of this Lie algebra that we just defined are the phi k's of the G. So if I'm interested in phi k's, I can get the phi k's from this holonomy Lie algebra. And then there's a really nice, so if you remember, when you take the universal enveloping algebra of a Lie algebra, Poincaré-Birkhoff-Witt says it has sort of a Hilbert series that looks like an infinite polynomial ring, roughly speaking. So this formula that we looked at when we put our phi k's in the numerator, that is the Hilbert series of the universal enveloping algebra of this holonomy Lie algebra. And then Shelton and Uzvinsky proved that this universal enveloping algebra is actually the Kazul dual to the quadratic OS algebra. So what's this quadratic OS algebra? I just forget all the relations in degree 3 or higher. So I have this relationship, and then, of course, you can compute these the dimensions of the diagonal tors are the same as the dimensions of the diagonal x's. And then what Arena proved, this was probably 15 years ago, was that this formula that we saw on the very first page, that I can get these phi k's for any hyperplane arrangement as these diagonal tors. So I don't need to be Kazul algebra or anything. It's always these diagonal tors. So the punchline is that if you're interested in these phi k's, and the topologists are interested in them, what you want to do is study not just the free resolution, but just the linear strand in the resolution of the residue field over the Orlick-Solomon algebra. So that is a good, I can't believe it. It's 11 o'clock. I never end on, I should keep on talking, so I go over time, so then everybody else is good. So this is this is the start of a question. So the question is going back. Let me go back. The questions that we're going to come to, I haven't given you guys good problems, but the bottom line is the questions are the following. So on the very first page, there's lots of open questions on what is the free resolution of the Orlick-Solomon algebra over E, and what is the free resolution of the residue field over the OS. And I'll go more deeply into these two things next time. One thing you can see right away is that, at least for this thing, the top strand, that looks pretty, everybody could guess the next number here, right? And so there's a conjecture on what this top strand looked like, and Dan Cohen and Alex Susiu and I were able to prove that conjecture. So these numbers for the exterior algebra are known, but the other ones are more mysterious, and that's a good place to end. So thank you very much.